let's get after it here. We're gonna start soldering some chips onto this board. So I've set this thing up with kind of approximately the layout that I want to have here on my board. I've thought quite a bit about how to do this, so I've intentionally kind of laid things out in this way. So first of all of our chips that we're going to use are going to go inside of these sockets. Okay, so anytime we use an IC, we're going to have a socket for that IC pretty much. The reason for that is that if the IC burns out, it's easy to just pull it out of the socket and stick a new one in its place. If we didn't have a socket, obviously we'd have to unsolder all the wires from the pins and and resolder them onto the new IC, and we don't want to do that, right? So it's easier to debug stuff and if you have everything in a socket. Okay, so we're gonna start out with just working with sockets for now. All right, so let me just kind of point out what we're gonna be dealing with here. This is the processor. It comes in a 68-pin PLCC package, and I have a 68-pin PLCC socket here. This is the clock. All right, the clock only needs 4 pins. This is our flash memory device. This is going to be a special socket for a flash memory device. It's called a ZIF socket, and what it allows us to do is just kind of set the IC in gently and lock it with this locking bar here so that we can easily pull the IC out to reprogram it. Okay, so this is going to be for our flash memory, and then this guy is going to be for our SRAM. Okay, so so if we want to remove one of these chips from the socket, usually we have to use kind of carefully use either some tweezers or a screwdriver or pliers or something like that to kind of gently pry it out of the socket, right? So normally for like the SRAM, we probably won't be cycling the SRAM in and out of there too much. We'll probably just stick one in and it'll probably stay in there for for forever, pretty much, unless there's something wrong with it. But obviously the flash memory, every time we want to program a new program onto the board, we're going to need to remove it, put it in the programmer, program the flash, and then stick the chip back in. So we're going to use this ZIP socket for our flash memory. See, it's a lot easier to pull the chip out. Okay, so chip orientation matters here. Okay, so I've oriented the device in a particular way. And I've sort of situated the other chips around it kind of carefully. Okay, so this is pin 1 of my PLCC device, my processor. Okay, my clock pin is on pin 16, which I think is over here somewhere. Okay, so we want to put the clock IC as close to the clock input on the processor as possible, because we don't want to have, this is going to be a 12 megahertz clock, right? And we want to have as short a wire as possible going from the clock over to the processor, so that we're not, so that we have a nice clean looking clock signal. Okay, so we don't. The first time I built one of these things, I put my clock IC way over here, on the far end of the board, and by the time the signal got routed, halfway across this huge board over to the microprocessor, the signal looked really ugly, right? And in fact, the board didn't even boot up because the signal was so ugly. Okay, so we want to put our clock real close to the CPU. All right, so the address bus and the data bus are going to be the interface from the microprocessor to the memory devices. Okay, and the address bus and data bus basically kind of live on these 3 sides of the chip, right? So pins, I think it's roughly pins like 30 through 68, and maybe pins 1 through 5 are in the data bus too. I can't remember exactly. You can check the data sheet for that. But basically, this is going to be, these 3 sides of the chip are going to be the address bus and the data bus, and those are going to be the interface to the memory. So we want to keep those, also kind of close to the memory if possible, because we don't want to be stringing wires a long distance. That's less critical though than the clock. The clock really does need to be a short wire. Okay, so this is all situated pretty close together here. I'm hoping that I don't live to regret the closeness of my of my chips. I'm hoping that this will be enough room to route my wires. On previous boards, you know, I've separated these quite a bit more. You know, I've had them like this far apart usually. Gives you a little bit more space to run wires, but the downside, of course, is it takes up more board space, and also, you know, there's the longer your wires, then the less clean your signals are going to look. Okay, so we'll go with this layout for now. Right. So let's just take one more look here at the bottom of this board. I'm gonna see if I can tape these. I got a piece of masking tape here I'm gonna use to just hold these guys in place while I flip the board over. Hopefully it stays. So if we look at the bottom of the board, it's probably pretty hard to see from the camera, but you can kind of see it. You see where you can see the PLC socket here, and you can see my clock. I don't know if you can really see that, but my clock is up here. I can barely see it actually looking at it. But I just want to make sure that, you know, this is going to be my my 5-volt bus here. This long interconnected string of holes on the top of the board, and I just want to make sure that the pins from my clock chip are not sticking through on this bus, right? I want to make sure I'm not, you know, I'm not using any of these buses, you know, the 5-volt buses or the ground buses for the holes for any of my chips. And it doesn't look like I am here, so I think I'll be in good shape. Okay, so so I guess we'll just get started mounting these chips, right? So all I need to do to get these chips to stick without masking tape is just solder a couple of the holes on each one of these guys here. And, you know, I guess we'll just do that. And they will stick to the board. So I'll fire up my iron. And I guess we'll start with the CPU PLC socket. Just want to make sure that socket is firmly pressed against the board when I solder the pins in here, this chip, and our SRAM socket. Cool. All right, so you can see I've got my tack solder joints set up there. I'm going to do a couple more in this PLC socket because it's wiggling a little bit. Actually, I'm just going to hold it up with this. My sockets are mounted. They're fairly stable on there. So I'm feeling pretty good about that. Oops, looks like I actually lost one of these pins at my PLC socket. It's sticking up here. It's not great. Not thrilled about that. It's not going to make good contact with my chip. Let's see if I'm going to just kind of heat that guy up quick and push it in. I'm gonna have to come back to that one. It's not good. Okay. Well, all right. Anyway, so we can start. We can start by hooking up power and clock for this guy. I'm going to use red wire for my power, and we're going to have pin 15 will be our one of our 5-volt power supplies here. So, okay, and be careful not to melt our pin. It's not too bad. All right, so that's going to be our 5-volt power, and that's going to come over here. This is my 5-volt bus. All right. So let me just cut this bad boy. Okay. Make sure that's gonna work. Right there. Restrict it a little bit more. That's perfect. So let me just bend this guy over and put him in right here. That's perfect. Let me trim it a little bit. Okay. So this is going to be my first power supply line on pin 15. I'm going to hook that up to this is my 5-volt bus here. So I'm just going to hook that up to this guy, right? So on the power supply bus, as we had talked about before, we're also going to put a 1/10 of a microfarad capacitor on every power supply input for every chip. Okay. So what I've done here, this is what I'm going to try to do. Just get a pointing tool to point out what I'm going to do. Okay, so here's my connection from my PLCC part. Let me see if I can kind of show this a little better. So this red wire is running from my PLCC part over to my 5-volt bus, right? And what I've done is I took my capacitor here and I dropped it through a hole, right, where one of the holes that I dropped it through is actually on this 5-volt bus, right? So I don't need to run a wire from this lead to my 5-volt bus because it's already, the hole that it's coming through is connected to the 5-volt bus. So I can solder that one right there. I'm going to do that now. Okay. The other side of this capacitor is going to go to ground. Okay. So we need to run a wire from this other lead of this cap that I just soldered up here over to ground, and this is going to be my ground bus over here. I'm going to use black for ground, so red's going to be for 5 volts, black's going to be for ground on this design. Let's see, I also have, do I have green? No, I don't have any green wire. If you have green wire, you can use that for ground too. I don't have green, so I'm using black. Okay, so I want to keep this as neat as possible because we're going to have a mess of wires when this board is all done. I want to have the minimum amount of mess. Okay, so here's my capacitor. Here's my 5-volt side of my capacitor and my ground side of my capacitor. And I can trim the leads on those. Okay, looks good. I can actually just fatigue the other lead off if I can do it here. There we go. Perfect. Looks nice. That's a good 5-volt bus connection here. So we'll do one more 5-volt connection. I think there's one more 5-volt pin on this processor. All right, so I have run my wires from my power pins over to power. Okay, so here's my first one here. That's pin 15, I believe, on the PLCC package over my 5-volt power bus, right? And I have my, somewhere in here, I have a, oh yeah, here's my decoupling capacitor, my 0.1 microfarad decoupling capacitor is right next to this guy right here, okay? And then on pin 53, I have run power over with a red wire from pin 53 over to my power bus. And then I also have run the same power line over to decoupling capacitor right here, which I placed, it's hard to see, I placed it right between the PLCC socket and the flash socket, okay? So, and then I hooked up my ground connection on pin 57 to the ground of the decoupling cap, okay? So I have 5 volts in ground across my decoupling cap, and I have ground run to pin 57, 5 volts run to pin 53, all right? And so this is good here, right? So what you can see is I've tried to keep my wires pretty short here. I don't want to have big excess of wires. If I cut my wire too long, a couple of cases I cut the wire, like the power supply wire, a little bit too long, and so what I did is I just trimmed it back, right? You don't want to have big hoops of wire here if you can avoid it, because what you'll end up is stuff will just get tangled up, right? You want to try and avoid having excessive amounts of wire on these boards. Now you don't want to run them too tight to the board either. You want to be able to kind of pry your wires up a little bit and get a little bit of space between the wire and the board in case you need to solder something onto these pins here. So you gotta be a little bit careful, all right? But it's a good idea to keep them as tight as possible, okay? And then, so the next thing we're gonna be doing is just running the ground from the PLCC package over to the ground bus of my, over the ground bus on my board. Okay. Okay, so I've soldered all the ground pins here now too. So we have a ground on 1, and then directly opposite to it, I believe that's pin 35. Then we have a ground pin on 17 and 18. Basically these two guys on 17 and 18, let me get it up a little closer to the camera so we can see it here. Basically what I did is I just daisy chained from 18 to 17, and then from 17 over to the ground side of this decoupling capacitor here that I'm using for the 5 volts. Okay, so here's my 5 volt decoupling capacitor, and I just daisy chained my ground from these 2 pins on 17 and 18 over to that decoupling capacitor's ground, and then that way I only have to run. I get 1, 2, 3 ground connections in this region of the board, but I only have to run 1 wire over to the ground bus. Okay. So this is fine. Usually on processors, you're gonna want to have a good ground, right? So that means you want to have thick wires running to the ground, right? In this case, I'm using pretty thick 26 gauge wire here for my ground connection, so I'm not worried about not having enough conductor running from my ground bus over to my processor. If I was using really thin wire, I would probably want to run multiple conductors over to my ground bus just to make sure that I have a solid ground connection on these 2 pins here, right? Okay, and then of course I have my other, I kind of did the same daisy chaining thing over here. I can't remember what pin this is, but basically I daisy chained from my microprocessor ground over to the ground terminal on my 5-volt decoupling cap, the one that lives right in between the 2 sockets here, right? So I daisy chain that over to this guy, right? So that way I'm trying to minimize the number of long runs of wire I have to do on this board, so it just doesn't get too cluttered, right? So that's my power, that's my power connection from my microprocessor. So next, I guess we can do the power connection for the memory chips and for the clock. All right, let's test this guy out now. now that we're done soldering up all of the power and ground connections to the clock and the chips. Okay, so the first thing we're gonna do here is just verify that we have a solid 5 volts. Okay, so I got my oscilloscope here, got my probe. All right, so this alligator clip on my probe is gonna go to my ground, and the tip of the probe is gonna go to the thing that I wanna measure. All right, so we'll start by, you're probably not supposed to really do this, but I'll just hook the ground up to my, to the screw that I'm using to screw the power supply down, and plug my power supply in there. All right, so I should have power on here. I just want to make sure before I actually stick any chips into any sockets on this thing, I just want to make sure that I have a good power connection. Okay, so I'll check my 12 volt side. So I'm gonna change my oscilloscope to be, let's see here. Change it to, we'll say 5 volts per division. Oops. And we will bring the voltage reference down a little bit. Okay, so we're at 5 volts. So each one of these boxes, the horizontal, or excuse me, each one of the vertical boxes is 5 volts, right? All right. So I'll just stick our probe on the 12 volt side of this, the input of my 7805 regulator, and we'll measure the 12 volt input. And you can see at the bottom in the middle there it says mean 12.40 volts, so we're happy with that. Okay, so we're at 12. We got 12 volts on the input. That's good. So let's change the vertical bars to, we'll say 2 volts per division. Okay, so my channel 1 is 2 volts per division, so each one of these vertical divisions here is going to be 2 volts. So 2, 4. So when we measure 5 volts, it should be kind of right in the middle of this, kind of like right where this trigger menu is pointing here. Oops. Okay, so let's check the 5 volt side here. So if I stick my probe on the output, I should have 5 volts, and if you look at the bottom center, it says mean equals 5.04 volts, so we're happy with that. Okay, so we have 5 volts on our power bus, which is good, okay? I'm gonna check that just to make sure we didn't actually accidentally short something out, and then we could end up frying something. Okay, so now we're gonna check our clock. So there's like a old saying among electrical engineers that, if your circuit isn't working, the two things you want to check are power and clock. Okay, so we need to make sure that our power is good and our clock is good. Okay, so we just checked power. So far, so good, right? So now we're going to check our clock. Okay, so here's my clock chip. This is a 12 megahertz clock. You can see it has let's see here. It's kind of hard to see with this thing, but there's all the corners are rounded but one, and the one I got my finger on there, that's the pointy corner. That's pin 1. Okay, so check the data sheet. If you got a different clock, check to see what the orientation is supposed to be. So this guy here is going to be pin 1, and then if you look on the IC socket that I have here, this little U-shaped thing, that goes toward the top of my chip. All right, and so then the pins are going to be numbered starting from here. So this is pin 1, 2, 3, 4. Okay, so the clock is special. The clock socket is special. 2 and 3 are empty, and 6 and 7 are empty, right? So we only have pins 1, 5, 6, and 8, right? Excuse me, 1, 4, 5, and 8, right? Okay, so we're going to put the clock in here, making sure that the corner here, pin 1, is going to be on the top left by pin 1 on the socket. Okay. One thing I forgot to mention about these other ICs here when I was putting them in is I noticed that I oriented all the U's in the same direction, right? So this U here is pointed kind of toward that side of the board. This is the U here for the flash chip, right? That's also pointing to that side of the board. It's a good idea to just keep all the, all the chips kind of oriented in the same direction. It'll just help make things easier when you're wiring stuff up, okay? Anyway, so all these are in the same direction. My clock is plugged in. Let's check to see what's going on here. So I'm gonna hook up my my scope probe to the ground. Well, that's the screw that's connecting the voltage regulator to ground. And here is my oscillator pin, right? The white wire, okay? And you can see if we look at our scope, it looks like we're getting a nice 12 megahertz signal here. I mean, I don't want to, whoop, hang on. Let me adjust the parameters of the scope here real quick. So I'm going to adjust the trigger level. This is my trigger level. And if you look, this is my trigger level indicator. And when I turn it, it's going to move the trigger level down. So I want the trigger level to be somewhere in the middle of this voltage signal here, right? So this is supposed to be a square wave. Yeah, that doesn't look too good either. Let me just move it down a little more. There we go. So the trigger level is now set to 3.12 volts, right? So let's try again. There we go. Okay, that's a stable looking signal. So that's supposed to be a square wave. It's a 12 megahertz signal, so it's not too surprising that it looks a little ugly, right? It looks maybe more like a sine wave than a square wave, but I think that's going to be good enough, right? We can't expect a high frequency signal to be, to be too square looking on a board like this. But since we kept the wire running from the clock chip over to the processor short, then it's gonna look decent. If that wire had been any longer, then that clock signal would look a lot worse. Okay, and we want it to look good enough, right? So that's good. I'm happy with that 12 megahertz clock.